So, good morning. So, today's topic is about an model development for us. Okay. So, when you are saying model development, so actually we have to define the structural modeling. So, already I said you that in the structural modeling, a model which is characterized by the basic model and the connection structure between these basic models will be there. So, first thing, so basic model in the sense by using the basic electronic components, for example, transistors, capacitors, everything that involved. Okay, so that has to be connected over on it, and which will be carried out between the thing over there. Okay, so the structural model which has be characterized by the basic model and the connection structure between these basic models over on it. Okay. Similarly, when you are defining the module, so that can be composed of again we'll have a basic models and it can itself be again connected to other modules. So this will be carried out. Okay. So this can be performed successfully. So which describes the complex system. Okay. So when we are characterizing the structural model, so we should concentrate on the following terms. So one to be the hierarchy, second one to be the modularity, third one to be the regularity, and fourth one to be the locality. So the structural model, which is characterized by the basic model, after composing of a basic model, it can itself be again connected to the other modules. So this will be successfully, which describes the complex systems. So this characterized on the four terms, one to be the hierarchy, second one to be the modularity, third one to be the regularity, and fourth one to be the locality. So how that hierarchy of a model? So it is derived from the whole structure of basic models and modules. Okay. So in the circuit diagrams, so in the case of a design, so using a circuit diagram editor, so modeling is primarily which is used for the derivation of a netlist, which is used as a circuit model. So incorporating the component or gate models. Okay. So that will be considering in the case of a circuit diagram editor. So we have to use the modeling which is used for the derivation of a netlist. So in this, which is used as circuit model, so we have to incorporate the component model. So actually this procedure is to be so simple. So and it is also unproblematic one. So the process of modeling a circuit it is not generally pursued as such over there. Okay. So this will be this has to be considered over there. Okay. So likewise, what will happen again? So there are not normally any problems with the validation of the circuit model. So there is no any problems with the validation of the circuit model. The field of applications is predominantly the development of analog circuits. The field of applications is predominantly the development of analog circuits over there. Although the digital circuits which can also be developed using circuit diagrams, that is the top-down design process which is only possible using behavioral modeling based upon hardware description languages. So already we said that. Okay. For example, we that seen analysis in the case of digital electronics. So we'll be simulation which is describable upon the hardware description languages overall. Okay. So the digital circuits which is used with the developed with the circuit diagram. For example, you take an ADA circuit, what will happen? So the combination of AND and OR gate. And an XOR gate. Okay. So that is similarly, so all the circuit diagrams so will be developed. Okay. And what approach we can able to use over on it? Being a top-down design approach is possible. How the top-down design approach is possible? Because the specifications and the systems will be defined and we'll be defining the module. So this is the module, this is the half adder circuit, this is the full adder circuit, this is the register, this is the counter circuit. So we'll be developing the system design. Then after that, we'll be defining the different modules. So in the full adder circuit, it consists of two different half adders. Okay, there is a different modules behind over on it. So then after that, we'll have a sub module. So in the half adder circuit, we'll be requiring all these components. So all this thing which will be developed by using only the top-down approach. The next one, state graph. So similarly, the digital systems which can also be represented by means of a state graph. So that is being slowed down relatively abstract models level. Okay. The selection of the state transition is precisely specified by the conditions over on it. So in the state graph, only the structure of the connection is necessary in order to characterize the model in the system. So such a model can, for example, be used for the specification of digital behavior, but it can also be translated into a programming or hardware description language. So and then used directly for the design of software and hardware. Okay. So which can be things over there. Okay. So when you are defining with the representation of state graph, so we have to with the system structure, then being slowed down relatively abstract levels. So the selection of the state transition, so which is specified by the condition. Furthermore, in state graphs, only the structure of the connections which is necessary in order to characterize the model in question. At the same time, for example, which is used for the specifications of digital behavior, or it can be translated into a programming or hardware description language, so which is used directly so that for the design of an hardware and software. On the next one, we'll be having about an multi-body diagram. So when we are saying a multi-body diagram, so things will be more complicated and we are going for multi-body mechanics. So although the importance of structural modeling is gaining increasing recognition over that, for example, the work of Pandrat, that is while drawing up the model equation, it is often the system as a whole, which is considered rather than leaving it as a collection of components. So only with the introduction of object-oriented modeling, so does the structural modeling of multi-body systems, which also becomes more prevalent one. Okay. So with the introduction of object-oriented modeling, so structural modeling of multi-body systems, which is the more prevalent one over there. Okay. So that is about the multi-body diagram. The next one we have to consider about the finite element. So in the case of finite element, a particularly graphic form of structural modeling, which is to break down the mechanical structures into finite elements for the modeling of continuum mechanics. So which is also called meshing over here, and both geometric dimensions and topological information which are important there. Okay. The element matrices of the individual finite elements which are found from their material parameters and geometry, whereas the connection structure between the elements and consequently the system matrix is derived from the topology. Often the meshing has to be checked manually in order to ensure that the elements of the correct form. The grid is sufficiently fine and available symmetries are exploited. Okay. So this is the case when you are saying about in the case of an finite element. So what we'll be doing? So we have to break down the mechanical structures into the finite element. So that is called as meshing. So in which both the geometric dimensions and the topological information that has to be considered over there. Okay. So this element matrices which are found from the material parameters and geometry, connections which also uh, derived from the topology. Okay. So once it has to be checked manually, so the grid is sufficiently fine and is available, symmetries or exploited. The next thing we have to see about an physical modeling. So in the case of an physical modeling, we'll be using a laws of physics, so which is used to describe the behavior and the interaction mechanism of a system or a component. Okay. The selection of this relevant relationships, which depends upon suitability and efficiency and the establishment of cause and effect chains over there. Okay. And it also requires a comprehensive understanding of the system and it remains an engineering task. So the customer support for this form of modeling is at best rudimentary and the perspectives of modeling. So we'll have a system perspective and we'll have a component perspective. Okay. Whereas in the case of a system oriented modeling, it formulates the system in the overall context. Whereas in the case of an object oriented modeling, it describes the components which only form a system by their connection together, that is by structural modeling. Okay. So the decisive factor is that in object oriented modeling, in no system, knowledge is fed into the component model. Okay. So this laws of physics, which is used to describe the behavior and the inner action mechanism of a system component. Okay. So perspectives of modeling, we have a two things, one to be the system perspective, another one to be the component perspective. So we know that system oriented, which formulates the system, whereas object oriented model, which describes the component. Okay. So now the decisive factor is to be that object oriented modeling because no system knowledge is fed into the component model. And experimental modeling. So experimental modeling, the mathematical models of dynamic systems, which is on the basis of measured data, or at least which provides existing models with the parameters. So neither the underlying physics nor the internal life of the system, which need necessarily play a vital role in model generations over there. In contrast to physical modeling, there are procedures for experimental modeling in which the modeling can be wholly or partially automated. Whereas in the case of a table model, the method of incorporating measured data is by the formulation of table models that lead to a script or piecewise linear characteristics. Whereas in the case of a problem, we'll have abrupt changes or links over on it. Okay? So the difficulties that are numerical in nature, since numerical oscillations may occur at abrupt changes and leaking. So possible solutions which is offered by procedures that smooth the characteristics, either we can go for an Chebyshev approximations or to be the spline approximation. So whereas in the case of an while you are estimating the parameter estimation or system identification, so the first thing we have to analyze the signal, then we have to specify the modeling method, then third thing we have to do the selection of the quality criterion, and finally calculations of parameters has to be done. So that is the sequence order I have shown over here. This is the system identification sequence. So whenever, so for example, if you are saying to be the when any signals which is passed over it, you have to analyze the signal. Then we have to specify the model, what model is going to over on it. And we have to select the quality behind over that and also the calculations. Okay. When you're having a system under investigation, so we'll have over here, see, so real time system, which is multiplied. So we know that we'll be using the summer over here. So in that summer, so if you are seeing up there, so what will happen? So this the nk, the output of product of yk is equivalent to the product of this value a into xk. Okay. So when you are seeing a model, which is also will be taking over that. So this is the comparison between the real systems and the model for the parameter estimation. So whereas here this one yk is equivalent to your a into xk plus your nk. So in the real system, this is the thing. Whereas in the model, what we have obtained now, we have obtained only a AXK. So what will happen? We have to check over this. So we have to check the quality, minimum quality over that. So that has to be verified again. So this is the system under investigation between the real system and the model estimation system. So quality will be summation k is equivalent to 1 e to the power of k2. So this will be simplified as an yk minus k because error we have a yk minus y complex k, whereas y complex k is nothing but an a dot into your x. Okay. So whereas when you're taking a transpose of this value, we know that. So what is the x transpose? What about the y transpose? What about the y transpose? E transpose. So quality, so we'll be having a e transpose into a e. So we'll have a y minus ax of whole part transpose into y minus ax. So this is will be y transpose y minus 2a y transpose x plus 8 squared x transpose into your x over here. So when you are seeing up there, so dou q by dou a factor is equivalent to minus 2y transpose x plus 2a cap x transpose x is equivalent to 0 and the a cap of is equivalent to y transpose of x by r x transpose of x. Okay, so this is the case we'll be taking over that. Okay, so the remaining topic that we can see in the next class. Thank you.